Yeah. So we are dealing with the equilibrium, right? So yesterday we have covered some topics from hydrolysis, and in that we have discussed the types of salts, etc., etc., right? And yesterday we have studied many formulas also. Today we are entering into the new topic called buffer solution. Okay, we are entering into the new topic called buffer solution. So here in this topic, we are going to cover the introduction to buffer solution and the two types of buffer, which are acidic buffer and basic buffer. Okay. So coming to the introduction to buffer, before entering into the main topic, we should know the importance, right? Importance of buffer solution. So that is what we are going to cover here in the introduction part. So what is the importance of buffer solution? So to know the importance of it, let me talk about the pH level of the blood. pH level of the blood. So can anyone tell me the normal pH level of the blood in terms of the pH values? Do you guys know the normal pH level of blood? The normal pH level of the blood? Okay, I will tell you. So here you see the normal pH value ranges from, Janvi, very good, very good. It is above, right? So your answer is correct, but not exactly. Okay. So here you see the normal pH value ranges from 7.35 to 7.45. So if it goes less than 7.35, it is called acidosis. I mean 7 to 7.35. And if it is between 6 to 7, it leads to death. In the same way, if it is between 7.45 to 7.8, it is called alkalosis. And beyond 7.8, it leads to death. Okay, so the pH level of the blood should be between 7 and 7.35 and 7.45. Got it? So now moving ahead with this, can anyone tell me the pH of urine? So what is the pH value for urine? Do you have any idea about it? The pH value for urine? Urine pH. Yeah, very good, Roshan. It is acidic. And the pH value is equal to 6. Okay, yeah. It is around 6. It is actually exactly 6. Got it. If the pH value decreases, if the pH of the urine decrease, then it is called as acidosis. Okay. So mostly starvation and dehydration will be there. And uncontrolled diabetes. Okay, it will lead to uncontrolled diabetes. Got it? In the same way, if the pH value increase, what will happen? So it leads to alkalosis, and here chronic renal failure will happen, and all types of urinary tract problems, obstruction will be there. Okay. So the control of pH is very, very important in many chemical and biochemical process. Okay. So whether the pH of the blood or the pH of the urine, it should be maintained properly. Okay. Otherwise, it will lead to many diseases. Got it. So moving ahead, we will discuss the definition of buffer solution now. So what is a buffer solution? The solution which resists change in pH on dilution or with the addition of small amount of acid or alkali are called as buffer solution. So what they are trying to say, a solution is there. And when do we call that solution as buffer solution? Let me take one solution, and here the pH of the solution is 5.5. Okay. So the first thing is, if I am diluting that particular solution, it will resist the change in pH. Resist means the pH value will not change. It will resist. pH value will remain same. So addition of water to this solution which has the pH of 5.5 will remain same as 5.5. So what it has done, the solution is resisting the change in pH on dilution. Okay. So those solutions are called as buffer solution. Students, am I audible? So there is a technical issue from my side only. So can you all able to see the screen? Am I audible? Roshan, Trisha, am I audible? Guys, can you able to hear my voice?
Yes, ma'am.
Mangtoi, Trisha, Roshan, is my voice audible to all of you?
Yes, ma'am.
Yes? Okay. So sorry for the interruption. We will go ahead. So what I was saying, the solution which resists the change in pH on dilution or with the addition of small amount of acid. So here I have added an acid and the pH has to reduce, right? It has to decrease on the addition of acid, but it remains same. Got it? And also, if I add some alkali, alkali means base, okay? So on addition of this base, the pH is going to remain same and it is not going to change. It is not going to increase. Got it? So whether I am diluting it or whether I am adding an acid or I am adding a base, the pH of the solution will remain unaffected and those solutions are called as buffer solution. Got it? Clear for all of you? So do you have any doubts? Shall we go for the types of buffer? Give me a thumbs up or say yes or no, say it is clear, say something so that I can understand that you guys are listening and watching. Huh? Do you have any doubts? Okay. So now coming to the types of buffer. There are two types of buffer as I have already told you. One is acidic buffer and the other one is basic buffer. Acidic buffer means the buffer solution which has the pH value less than 7. So in the previous case, in the picture I have shown you, right, one solution with the pH value 5.5. So 5.5 is less than 7. So that solution is an example for acidic buffer. Got it? So acidic buffer solutions are prepared by mixing the weak acid and its salt with the strong base. This point is very important. It is prepared by mixing weak acid. Okay. So there are two components. One is a weak acid. Got it? What is an example for weak acid? Yesterday I asked you to remember the example for weak acid, weak base and strong acid, strong base, right? So what is the example that I gave for weak acid? Can you guys tell me? Let me see who is remembering the concept. What is an example that I gave for weak acid? What is the example for weak acid which we have studied yesterday? Acetic acid. Yeah, okay. CH3, COOH. CH3, COOH is the example I gave for weak acid. Then it's salt with the strong base. It means weak acid salt. Weak acid salt means CH3COOH. And if this weak acid is reacting with the strong base means NaOH, okay? If they react, they will form a salt, right? So H2O will go out and they will form a salt. CH3COO minus and Na plus salt they will form. Got it? So what they are trying to say? It is prepared by mixing a weak acid and its salt, weak acid salt with the strong base. Okay. So these two components are mixed together and they form a buffer solution, and those buffer solutions are called as acidic buffer solution. All right. So the example is the mixture of acetic acid and sodium acetate. Got it? Now coming to the second type, which is basic buffer. So the buffer solution which has pH value greater than 7 are called as basic buffer solution. Okay. And it is prepared by mixing a weak base. So what is the example for weak base? NH4OH. Okay. And it's a salt with the strong acid. It means NH4OH salt. Okay. Weak base and it's salt with a strong acid. Strong acid example is HCl. Okay. And on removal of this water, it will produce a salt of formula NH4Cl. Okay. So this is the salt. This is the salt. So weak base and its salt with the strong acid. Got it? So when these two components are mixed with each other, they will form an example for basic buffer solution. Got it? So do you have any doubts here? Do you have any doubts here? Can you able to understand? Okay. So now let's go in detail about the acidic buffer. Okay. So you all know what is an acidic buffer, right? It is prepared by the weak acid and its salt with the strong base. If the weak acid formula HA ionizes in water, what will be the reaction? Let me take some acid of formula HA and let me treat it with water. And it will be in equilibrium with H3O plus and A minus. Got it? So the pH for such type of system will be equal to pKa plus log of concentration of the conjugate base by the concentration of the acid. So this is acid. HA is actually acid and water here will act as a base. Okay. And this is the conjugate acid and this is the conjugate base. So in the formula, we are writing the conjugate base in the numerator and the acid in the denominator. Got it? So the pH will be equal to pKa plus log of conjugate base, concentration of the conjugate base divided by concentration of an acid. And as you can see, this is called as Henderson-Hasselbalch equation, which is very, very important. Okay, for acidic buffer, pH has to be calculated using this formula. And this formula is called as Henderson-Hasselbalch equation. Okay, so let me take this Henderson-Hasselbalch equation and let me talk something about it. Okay, it is the conjugate base by acid. Most of the conjugate base comes from the ionization of salt of the acid. Ionization of the salt of the acid, right? So in the previous case also what we have studied, this particular conjugate base has come from the ionization of this acid. So HA got ionized and they produced H plus and A minus, right? So this is the conjugate base and it has come from the ionization of the acid. So that is what is written here. Got it? So the pH can also be found out using pKa plus log of salt concentration divided by acid concentration. Okay. So we can take the concentration of conjugate base or we can take the concentration of salt. Got it? if the concentration of the salt and acid are same, if the concentration of acid and the salt, if both are equal to 1, for example, then the case will be pH is equal to pKa, because 1 by 1 is equal to 1. So what is log 1 value? Log 1 is equal to 0. Got it? Even if I have 2 also, if both are 2, then 2 by 2 is equal to 1. So log 1 will be 0. So we are left with only pH, which is equal to pKa. Got it? So if the salt and acid are having the same concentration, then pH is equal to pKa. If we prepare a buffer solution by mixing acetic acid and sodium acetate, this is the formula for sodium acetate in equal concentration, then this solution has pH which is equal to 4.76. So this value is for this particular mixture. Okay, this particular mixture. So it is acidic in nature and the pH value is 4.76. Got it? Clear? So now we have spoke about the acidic buffer in this slide and the previous slide, and I gave you two formulas to find out the pH for acidic buffer. And also one example we have taken, and it is said that pH for that particular example is 4.76. Okay. So now we will study the buffer action of this acidic buffer. So this is the example which we took from the beginning of this acidic buffer solution, right? So let me discuss about the buffer action of this acidic buffer system. Okay. So now I have a container, and inside the container we have the weak acid, which is acetic acid. Okay, these are the acetic acid, and the salt we have CH3CO minus Na plus salt. So Na plus cation and acetate anion, everything is present inside the container. Also, we have H3O plus. We also have H3O plus because it is put inside the water, right? So we have water molecule and it takes the hydrogen. So we get H3O plus also. And this is the buffer solution of this two combination. And when the weak acid reacts with the water, when it reacts with the water, it produces H3O plus and CH3COO minus. Okay. And these are the H3O plus which has come from this particular equation. Got it? So, and also it has the acetate ion. It also has the acetate ion. So now, having this in your mind, so do you have any doubts till this? Do you have any doubts till this? So I have taken one example for the acidic buffer solution, and in that I have acetic acid, also the salt. Okay. So acidic acid will react with the water molecules which are already present inside the container, and they produce acetate, new acetate ion and the H3O plus. Do you have any doubts till this? Shall we go ahead? Yes. So here you see there are going to be some cases. First is case number 1. If we add small amount of strong acid like HCl to this system, you see here, like HCl to the system, what will happen, they produce CH3COOH and H2O. Okay. So this H3O plus has come from the strong acid which I have added, because HCl will have H plus and Cl minus, right? So it has H plus ion, and that H plus will react with the water which is already present inside the container, and they produce H3O plus. And this is already present inside the buffer, and we are getting a weak acid. We are getting a weak acid. Got it? So this weak acid formed is which is less ionized. Weak acid formed is which is less ionized. So pH of the buffer solution is not changed. So this weak acid, what is the meaning of weak acid first of all? The one which undergoes partial dissociation. right? Partial dissociation means they will not get ionized completely. Okay, so it is less ionized. The weak acid which has formed by the addition of strong acid to the solution is less ionized, so the pH of the solution will not change. Clear? This is case number 1. This is case number 1. Then coming to case number 2. So here I am going to add a base. So base is sodium hydroxide and it has Na plus and OH minus. So the OH minus of the base will react with the acetic acid and it forms acetate ion and water. So this OH minus has come from the base and this acetic acid is already present inside the buffer solution as one of the component, right? So the two components, acetate ion and water formed, so pH of the buffer solution is not changed. It is producing the water and the acetate ion. So there is no change in the pH. Okay. Clear? OH minus ion is not going to take part in this. So the pH of the solution will not increase. Got it? So these are the two cases. So on addition of a strong acid or addition of a strong base. So both of them are not going to affect the pH, and the explanation I gave you for this. Okay. Do you have any doubt here? Shall we go ahead with one question? Shall we go ahead with one question? OH minus concentration or H plus concentration. It is not there in the solution at all. So it will not increase the pH, neither it will decrease the pH. Got it? So I will go ahead with one question. A buffer is prepared containing 1 molar acetic acid and 0.8 molar sodium acetate. Okay. What is its pH? What is its pH? pKa for acetic acid is 4.752. So how to approach this? Acetic acid concentration is given. Sodium acetate concentration is also given. CH3 COOH concentration is given and CH3 COO concentration is given. Okay, this is the salt and this is the weak acid. Got it? What is its pH? pKa is also given. So how to approach this, students? So which equation you will use? Henderson-Hasselbalch equation, right? So from Henderson-Hasselbalch equation, we know that pH is equal to pKa plus log of concentration of the salt divided by concentration of the acid. So what is the concentration of the salt? 0.8 and the concentration of acid is 1 molar and the pKa value for acetic acid is 4.75. Okay. So you have to do the calculation here. So it is log 0.8 minus log of 1. Okay. So if you have log A by B type of thing, it should be equal to log A minus log B. Got it? So now you can have this log 0.8 value is around 0.09 kind of thing and log 1 is equal to 0. Log 1 is equal to 0. So just have the value of log 0.8 alone, which is 0.097 and subtract with the pK value and you will get the answer as 4.655 as the pH value for this equation. Clear? Able to understand? Yeah, what about others? What about others? Trisha, Vangtoi, Mahesh Babu? Some JNV students. I don't know from which JNV you guys are. So shall we go ahead with the basic buffer? Shall we go ahead with the basic buffer?
Yes, ma'am.
Okay. Basic buffer. So what is a basic buffer? It is prepared by mixing a weak base and its salt with the strong acid, right? So if the weak base like BOH formula ionizes in water, they will produce B plus ion and OH minus ion. So for such type of system, we can find out the POH. Like pH, we can find out the POH, and it is equal to pKb plus log of concentration of B plus divided by concentration of the base. Okay. So this is the base, this is the conjugate acid, and this is the conjugate base. So POH is equal to pKb plus log of conjugate acid divided by the concentration of the base. And this is the Henderson-Hasselbalch equation for basic buffer. This is the Henderson-Hasselbalch equation for basic buffer. Okay, POH. POH is equal to pKb. And coming to, so let me take this formula. And here, most of the acid, conjugate acid comes from the ionization of the salt of the acid. So instead of writing the conjugate acid, I can write it as a concentration of the salt. Okay. And also we know that pH is equal to pKw minus POH. So from where did we get this formula? We have studied ionic product of water in one of the previous class, right? So there I have given like pH plus POH is equal to pKw. Okay. So from this pH is equal to pKw minus POH. So from this only we are getting this equation. Got it? So the pH will be equal to pKw minus POH. So we know what is POH. So it is here. So substitute this value or this value. Okay, anything is fine. So substitute this value of POH here in the formula and you will get one more formula. Okay, you can use this formula also. Now, at 298 Kelvin, pKw is equal to 14. We have already studied this. At normal temperature, at room temperature, pKw is equal to 14. So, pKw value is becoming 14 at 298 Kelvin. So, we can substitute that and get one more relation. Got it? So, these are the relations which we are learning from the basic buffer. So, the very important relation is in terms of conjugate acid, you can use this first formula. In terms of the concentration of the salt, you can use the second formula. And in terms of pKw, you can use the third formula. And putting the value of pKw at 298 Kelvin, you can use the fourth formula. Okay. So now we will take the example. If we prepare a buffer solution by mixing ammonia solution and ammonium chloride in equal concentration, then its solution has pH of 9.5. Okay, ammonium chloride is a salt. Ammonia is a base. Got it? So, for this particular buffer solution, we have the pH value as 9.25 because it is a basic buffer, right? It should be greater than 7. So, for this particular example, the value is 9.25. Okay. So now I am going to give you the buffer action of basic buffer. Buffer action of basic buffer. So I have taken ammonium hydroxide and ammonium chloride as the example for you. Ammonium hydroxide is a weak base. Ammonium hydroxide is a weak base. And this is the salt of this weak base. Okay, salt of this weak base and strong acid. Got it. So now in the container, I am going to have the weak base and its salt. Weak base means there won't be any dissociation, right? Partial dissociation occurs. So NH4OH remains same And the salt will have NH4 plus ion and Cl minus ion. Okay, Cl minus ion. So those ions are there inside the solution. This is the buffer solution of NH4OH and NH4Cl. Okay, so the NH4OH, if they undergo partial dissociation, they produce NH4 plus and OH minus. Got it? So that OH minus is here inside the solution. Now, coming to the cases. If I add small amount of strong acid like HCl to this, already we have the weak base and the H plus is coming from the strong acid which I have added. So they will react with each other and they will produce water and the ammonium ion. So the H plus is coming from the acid and the weak base NH4OH is already present inside the buffer. Okay, it is already present inside the buffer and they produce ammonium cation and water. Okay, so we don't have H plus ion in the resultant solution. So the basic buffer pH will not change. Okay, so we get NH4 plus and H2O formed as a product. So the pH of the buffer will not change. In the same way, if I add some amount of base, if I am adding a strong base like NaOH, the pH is not going to get affected. Why it is not going to get affected? The OH minus which is present in the strong base which I am adding will react with the ammonium ion and they produce ammonium hydroxide and water. Okay, so the OH minus has come from the strong base I have added and NH4 plus ion is already present inside the buffer solution. So they produce a weak base and water. Okay, and this weak base which has formed is very less ionized. It is actually less ionized because it is a weak base. So it cannot get separated into NH4 plus and OH minus. Okay, weak base means dissociation will not occur properly. So the ionization will be very less. Okay, so the production of OH minus will decrease and it will not happen at all. Got it? Only if the OH minus ion concentration increases, the pH of the basic buffer solution will increase. Okay, but here we are not getting any OH minus ion at all in the final product. So there is no use of adding the small amount of strong base or strong acid to the solution. Got it? The pH value will not change. Clear for all of you? Do you have any doubts? So the thing is, by adding an acid or a base, acid means finally in the solution we should have H plus ion, right? If I am adding a strong base, I should have OH minus ion. Okay, only if the H plus and OH minus concentration increases, we can say that the solution is becoming acidic or it is becoming basic. Okay, but the ions, the H plus ion and the OH minus ion that is getting produced from the acid and base which we are adding is reacting with the ions which is already present inside the solution. Okay, and they produce products like this and they produce a product like this. So there is no presence of H plus or OH minus to decrease the pH or to increase the pH. So that is why the pH value remains unaffected. Clear for all? Any doubt? So do you have any doubts here? This is all about the buffer solution. So let me summarize what we have studied, okay? So first I gave you the definition for buffer solution. So it is a solution which resists the change in pH on addition of water or addition of acid or addition of a base, right? Acidic buffer is prepared by weak acid and its salt with a strong base. And also we have studied the Henderson-Hasselbalch equation for acidic buffer solution. And next, coming to basic buffer, it is prepared by weak base and its salt with a strong acid. And then Henderson-Hasselbalch equation for basic buffer solution is POH is equal to pKb plus log of salt by base. Okay, so these are the points you have to keep in mind from the buffer solution topic. All right, clear? Clear? Shall we go ahead? Shall we go ahead with the next topic? Yeah. The next is solubility product. Next topic is the very last topic of this lesson, solubility product. So here we are going to see what is solubility equilibria, and then we are going to learn how to write the expression for the KSP. Okay, we will learn what is KSP. So don't worry. And also we will see the effect of common ion on solubility. The effect of common ion on solubility. So first, let me enter into the first topic, which is solubility equilibria. Solubility equilibria. So to understand some of the concepts which are coming under solubility equilibria, we should know the meaning of lattice energy and hydration energy. Okay. So let me explain you what is lattice energy and what is hydration energy. So we have already studied the definition for these two terms in the thermodynamics lesson, but still let me revise it. Okay, let me revise here so that you can understand it better. So what is lattice energy? The energy required to break 1 mole of the ionic compound. Ionic compound means I can take NaCl. So NaCl should be present in its solid state form to get converted to, and they will get converted to free gaseous ion. The energy required to break 1 mole of the compound in solid state to form the free gaseous ions is called as lattice energy. Okay. So see, I have taken NaCl lattice. It is in the solid form and it is present in its present as 1 mole, and this 1 mole of NaCl is producing Na plus ion and Cl minus ion, and both of them are gaseous ions. Got it? This is NaCl lattice, and after giving some energy, they are producing Na plus and Cl minus. Got it? So this is an energy absorption process because it is a bond breaking process, right? Bond breaking processes are always endothermic in nature. Okay, they are endothermic in nature because they absorb the energy and the delta H value will be positive. Okay, so we have plus 787 kilojoule per mole of energy to break the entire lattice. So this much of energy is absorbed by the NaCl lattice to be broken down. And this is called as lattice energy. The second term is called as solvation enthalpy or hydration enthalpy. Okay, solvation energy or hydration energy. So what it is? What is this? It is the enthalpy change when 1 mole of the substance or ion is completely hydrated by water. Okay, so let me take an ion. Let me take the same sodium cation and let me treat it with X moles of water. So what will happen? The gaseous ion will be converted to aqueous ion. Gaseous ion is changing to aqueous ion, okay, by taking the water molecule. So the free gaseous ion is reacting with the polar water molecules and they produce the hydrated ion. So the negative end of the water molecule is forming the bond with the free gaseous ions, okay. And here bond formation occurs. And here bond formation occurs between water and the free gaseous ion. Bond formation means it is exothermic reaction. So during the bond formation, energy will be released. Energy will be released and the delta H value will be negative. Got it? So this is an exothermic reaction and the hydration energy value is minus 406 kilojoule per mole. Got it? So can you able to understand what is lattice enthalpy and hydration enthalpy? So moving ahead with these two definitions, let's see what is solubility. It is the maximum amount of solute that dissolve in 1 unit volume of the solvent at a given temperature and pressure. So the maximum amount of solute that can be dissolved in a specified amount of solvent is called as solubility. Okay. So I may have 1 liter of water. I may have 1 liter of water in a container and this is a solvent. Okay. So let me take a sugar molecule. Okay. Let me add some in 1 liter. How many? So let me take 50 gram. Let me take 50 gram. So I am going to add 50 gram of the sugar and the sugar is a solute here. Okay. So the maximum amount of sugar that can be dissolved in the 1 liter of water is 50 gram. Okay. If I add more than 50 gram, let's say it will not get dissolved. Okay. Then we don't call that a solubility. So the maximum amount of solute that can be dissolved in a specified amount of the solvent is called as solubility. Okay. So here, if the lattice enthalpy is less than the hydration or solvation enthalpy, then the given salt will dissolve. So we do not know how many grams has to be added in the particular amount of solvent and all, right? So we are using the delta H value, hydration enthalpy value and the lattice enthalpy value. If the hydration enthalpy value is more, then the particular salt will get dissolved. Okay. If the hydration enthalpy is less, then the salt will not dissolve. So this is how we are going to calculate the solubility using the lattice enthalpy and the hydration enthalpy values. Got it? Clear? So shall we go for the next slide? Shall we go for the next slide? Can you all able to understand the difference between lattice enthalpy and hydration enthalpy? Yes? So, let me just discuss about the classification of salt on the basis of solubility alone. And then we will discuss the remaining thing in the next class. Okay. So now the classification of salt on the basis of solubility. So first category number 1. If the solubility is greater than 0.1 molar, then the given salt is soluble. Okay. If the solubility is less than 0.1 and greater than 0.01, then the given salt will be slightly soluble. Okay. If the solubility is less than 0.01, then it is sparingly soluble. Sparingly means partially soluble. Okay. So this is how we classify the salt on the basis of solubility. Okay. Using the concentration values. Using the concentration values only, we are finding out whether the particular salt will get dissolved or it will not get dissolved or it will sparingly soluble or slightly soluble kind of thing. Okay. So this is all about the solubility equilibria. So we are left with 2 more topics in this last topic of the lesson. So that we will discuss in the next session. Okay. So do you have any doubts here? Do you have any doubts in today's session? So please go through the buffer action, buffer solution topic. Okay. So we will meet next week. Okay. We will meet next week. So till then, take care. Okay. Have a nice weekends. Have a nice holiday. So enjoy your days and we will meet up in the next class and next week. Okay. Till then, take care. Bye-bye.